Before studying thermal equilibrium, we need to know what thermodynamics is. Thermodynamics is the study of exchange of heat and work between a system and its surroundings, and the resultant changes in the macroscopic variables of the said system. In thermodynamics, we deal with the macroscopic thermal properties of a system without knowing its internal structure. A thermodynamic system is an isolated body or a group of bodies with a well-defined boundary. It is important to identify the system, its surroundings, and the boundary that separates both of them. Some thermodynamic systems are as shown. Gas in a closed container is the system. The walls of the container act as the boundary. The environment acts as surroundings. Refrigerant is the system. The walls of the coil acts as the boundary. The compartment of the refrigerator acts as surroundings. The fuel inside an engine is the system. The walls of the engine are the boundary. Environment acts as surroundings. A thermodynamic system can exist in different states. The state of a thermodynamic system is identified by its macroscopic variables such as mass, pressure, volume, temperature, entropy, and enthalpy. For example, consider a given mass of gas at pressure P1, volume V1, and temperature T1. The state of a gas is identified by providing these values P1, V1, T1. If the gas is compressed, these values are changed to P2, V2, and T2. Then the new state is identified by P2, V2, T2. The state is said to be in equilibrium if there is no change in any of the macroscopic variables that distinguish the state with time. A system of gas in a container is said to be in equilibrium state if the pressure, volume, and temperature of the gas do not vary with time. The state of a system changes if the system exchanges heat with its surroundings, or when work is done by the system, or when work is done on the system. Whether a thermodynamic system can exchange heat energy with its surroundings or not depends on the nature of the boundary. An adiabatic wall does not allow any flow of heat through it, whereas a dithermic wall allows the flow of heat through it. That means an adiabatic wall acts like an insulating wall and a dithermic wall acts like a conducting wall. Consider a container with two chambers A and B separated by a partition. Take two gases in the two chambers, gas A and gas B. The state of a given mass of gas can be completely expressed by independent variables, pressure and volume. Let the initial state of the gas in container A be PA, VA, and that of the gas in container B, B, PB, VB, and the walls of the container and the partition between the chambers are adiabatic. As time passes, since the walls and the partition between the chambers are adiabatic, there will be no change in any of the macroscopic variables of either gas A or gas B. Let's retain the adiabatic wall as it is and replace the adiabatic partition with a diathermic material. Now, exchange of heat energy takes place between gas A and gas B, and as a result, there will be changes in their macroscopic variables. After sufficient time, they will settle at different equilibrium states, PA', VA' and PB', VB', and there will be no exchange of heat energy between them. We say that the two systems are in thermal equilibrium. Two systems, A and B, are said to be in thermal equilibrium when 1. They are in contact with each other or separated by a diathermic wall, and 2. The state of system A is in equilibrium with the state of system B. What will happen if we retain the adiabatic partition between the two chambers and replace the insulating walls with diathermic walls? After sufficient time, gas A and gas B will attain different equilibrium states. But as the walls are diathermic, gas A and gas B are in thermal equilibrium with the surroundings. If we replace the adiabatic partition between the two chambers with a diathermic partition, then there will be no flow of energy between gas A and gas B. Because when two systems, A and B, are individually in thermal equilibrium with a third system C, they are in thermal equilibrium with each other. This is known as the Zeroth Law of Thermodynamics. Now, if we measure the temperature of all the three systems, we find all of them at the same temperature. This fact is used to define temperature. Temperature is the macroscopic variable that is equal for both systems when they are in thermal equilibrium. Consider two thermodynamic systems, say gas A and gas B, which are in two chambers of a thermally insulated wooden box and separated by a metallic partition. Let the initial temperatures of both gases be T1 and T2, with T1 greater than T2. We know that after sufficient time, they attain thermal equilibrium. Basing on this observation, temperature is defined as a thermodynamic variable that is equal for systems in thermal equilibrium. Systems at different temperatures and in thermal contact attain thermal equilibrium because heat flows from a hot system to a cold system. An important point to note about heat is that it is energy in transit. It exists as a flow only. A question like, how much heat does a sample of gas contain, has no meaning. In thermodynamics, the energy possessed by a system is internal energy, usually denoted by U. The internal energy of a system is the macroscopic thermodynamic variable that changes when it either emits or absorbs heat energy. For example, ice at 0 degrees Celsius converts to water at 0 degrees Celsius by absorbing heat energy. Though there is no change in the temperature, the internal energy of ice increases when it is converted to water. On the other hand, if water at 30 degrees Celsius is heated to water at 60 degrees Celsius, both the temperature and internal energy of water increases. At a microscopic level, the internal energy of a system is defined as the sum of kinetic energies of all its constituent molecules due to their translational, rotational, and vibrational motions, and the potential energies due to the interaction between these molecules. An important point to be noted is that the kinetic energy associated with the motion of the center of mass of the system does not influence its internal energy. Similarly, the internal energy does not include the potential energy due to the interaction of the system with its surroundings. For example, take a system of gas in a container placed at a certain height. If the container is dropped, the kinetic energy of the center of mass of the system increases, but there will be no change in the internal energy of the gas. The gravitational potential energy of the system is greater when it is at a certain height than when it is on the ground. But the internal energy of the system is the same in both cases. Let us now look at another example in our daily lives. We all are familiar with the fact that our hands become warmer when we rub them together. Though there is no external supply of heat energy to the hands, the work done due to the friction between the hands makes them warmer. This implies that the internal energy of the hands, considered in this case as a system, is increased by doing work. That means that by doing work, we can change the internal energy of a system. Let us now consider a mass of gas enclosed in an airtight container with a movable piston as a system. Now compress the gas by exerting an external force on the piston. This can be done by placing some weights on the piston of the container. We can observe rise in the temperature of the gas. When the gas is compressed, the external force due to the weights did some work, and as a result, the internal energy of the gas is increased. That means that when work is done on a system, its internal energy increases. Now, by removing the external force on the piston, if the gas is allowed to expand, the temperature of the gas decreases, indicating a reduction in its internal energy. Hence, when work is done by a system, its internal energy decreases. That means we have two different ways of changing the internal energy of a system. One by allowing the system to exchange heat with its surroundings, and the other by allowing it to do some work. In thermodynamics, heat and work are the two modes of energy transfer to a system. Heat and work are not state variables. They depend on the path through which the system is taken. For example, consider a given mass of gas at an initial state described by P1, V1, T1. Let us plot a pressure versus volume diagram for the gas and identify the initial state of the gas as A in the PV diagram. Let us take the gas to a new or final state, described by P2, V2, T2, and identified by D in the PV diagram. We shall take the system from the initial state A to a final state D in two different ways. In the first method, place the container of gas on a hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure. After sufficient time, the gas may be at a new state, identified by P1, V1-T2, and represented by point B in the PV graph. The curve AB represents the process of changing the state of the gas from P1, V1, T1 to P1, V1-T2. Now, keeping temperature constant, compress the gas by placing a weight on the piston to the final state P2, V2, T2. This change in the state from P1, V1-T2 to P2, V2, T2 is represented by a curve BD in the PV graph. In the second method, compress the gas by placing some weights on the piston and change the initial state of the gas P1, V1, T1 to a new state represented by P2, V-T1. In the PV graph, the new state is represented by C and the process by the curve AC. Now place the container on the hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure to reach the final state P2, V2, T2. This process is shown by the curve CD in the PV graph. In this experiment, we have taken the system from its initial state P1, V1, T1 to a final state P2, V2, T2 by two different parts represented by ABD and ACD. Heat exchanged by the system in taking it from A to B and then from B to D is different from the heat exchanged in taking it from A to C and then from C to D. Even the work done by the system in taking it from A to D through ABD is different from the work done when taking it through ACD. In this aspect, the internal energy is different. Internal energy is a state variable. The internal energy of a system depends only on its state and is independent of the path through which it is taken. For example, in the experiment described earlier, let the internal energy of the system at its initial state P1, V1, T1 be U1 and the final state P2, V2, T2 be U2. Whether the system is taken through ABD or through ACD, the internal energy of the system in its final state remains U2 and is thus independent of the path followed. You have already learned that there are two different ways to transfer energy to a system. One is by heating the system, and the other is by doing some work on the system. The internal energy of the system may change during this exchange of energy with the surroundings. The relationship between the three important physical quantities, heat, internal energy, and work, is expressed by the first law of thermodynamics. The first law of thermodynamics states that the change in the internal energy of a system is equal to the heat absorbed by the system minus the work done by it on the surroundings. Consider a system of a given mass of gas in a container with a movable piston. When the gas is heated, let the heat energy absorbed by the gas be delta Q, and the work done by the gas while expanding be delta W. During this entire process, if the change in the internal energy of the gas is delta U, then, according to the first law of thermodynamics, delta U is equal to delta Q minus delta W, or delta Q is equal to delta U plus delta W. Note that the first law of thermodynamics is an expression of the general principle of conservation of energy. It is important to note that both delta Q and delta W can be positive or negative. If heat is absorbed by the system, then delta Q is positive, and if heat is emitted by the system, then delta Q is negative. Similarly, if work is done by the system, then delta W is positive, and if work is done on the system, then delta W is negative. What is the work done by the system? Let us derive an expression for the work done by considering gas in a container with a movable airtight piston of cross-sectional area A as a system. Let the pressure of the gas be P. Then, the force exerted by the gas on the piston F is equal to PA. If we assume that the force has pushed the piston through a small distance delta x, then the work done by the gas is denoted by delta W is equal to F into delta x, which is equal to PA into delta x or P into A delta x. But A delta x is the small change in the volume of the gas that can be denoted as delta V. Hence, the work done by the gas is denoted by delta W is equal to P into delta V. Let this be equation 1. In terms of differential calculus, equation 1 can be written as dW is equal to PdV. Let this be equation 2. Now, if we consider the expansion of the gas from its initial volume of V1 to a final volume of V2, then the total work done by the gas can be written as W is equal to integral dW between the limits V1 and V2, which is equal to integral PdV between the limits V1 and V2. Let this be equation 3. Though we have taken a gas in a regular shaped container to derive equation 3, this equation for work done by a thermodynamic system is applicable to solids and liquids as well. We can also apply this equation in phase changes. If a thermodynamic process is represented by a pressure P versus volume V graph, then the work done by the system can be graphically found. If during a process the volume of the system changes from V1 to V2, then the work done by the system is the area bound by the PV curve and the V-axis. For the given range of change in the volume of the system, let us apply the law to solve a problem. If 1 kilogram of ice at 0 degrees Celsius melts to water at 0 degrees Celsius at normal atmospheric pressure, what is the change in its internal energy? Given that the density of ice and water are 920 kilograms per cubic meter and 1000 kilograms per cubic meter respectively, and the latent heat of fusion for water is 335,080 joules per kilogram. Given mass of the ice m is equal to 1 kg, density of the ice d I is equal to 920 kg per meter cube. Density of the water dW is equal to 1000 kg per meter cube. Latent heat of fusion LF is equal to 335,080 joules per kilogram. On absorbing heat, the ice melts to water. If the heat absorbed by the ice is delta Q, then delta Q is equal to M into LF, which is equal to 335,080 joules. Let this be equation 1. If the volume of ice and water are represented by VI and VW, then VI is equal to M by DI, which is equal to 1 by 920, which is equal to 1.08 into 10 power minus 3 meter cube. Similarly, VW is equal to M by dW, which is equal to 10 power minus 3 meter cube. Therefore, the change in the volume delta V is equal to VW minus VI, which is equal to minus 0.08 into 10 power minus 3 meter cube. Let this be equation 2. As the melting of ice has taken place at atmospheric pressure P equal to 1.013 into 10 power 5 Pascal, the work done by the system in the process delta W is equal to P delta V, which, on substituting the values and simplifying, gives minus 8.104 joules. Let this be equation 3. Now we can apply the first law of thermodynamics to find the change in the internal energy of the ice. As per the first law of thermodynamics, delta U is equal to delta Q minus delta W. Substituting the values of delta Q and delta W from equations 1 and 3 and simplifying, we have the change in internal energy delta U is equal to 335,088.1 joules. Earlier, you studied that gases have two types of molar specific heat capacities. One is Cp, the molar specific heat capacity at constant pressure, and the other Cv, the molar specific heat capacity at constant volume. Now let us use the first law of thermodynamics to derive the relationship between Cp and Cv for an ideal gas. Consider a sample of mu moles of an ideal gas in a container with an airtight movable piston. On heating, the gas expands at constant pressure. Let the heat absorbed by the gas be delta Qp, where the subscript P indicates that the heat absorbed is at constant pressure, and the change in temperature is delta T. Then, delta Qp is equal to Cp into mu into delta T, or delta Qp by delta T is equal to mu into Cp. Let this be equation 1. For a change in temperature of delta T, if the change in the internal energy of the gas is delta U, then, as per the first law of thermodynamics, we have delta Qp is equal to delta U plus P delta V, or delta Qp by delta T is equal to delta U by delta T plus P into delta V by delta T. Let this be equation 2. But we know that for an ideal gas, PV is equal to mu RT. If we apply this law to the above process, we have P delta V equal to mu into R into delta T, or P into delta V by delta T is equal to mu into R. Let this be equation 3. On substituting the values from equations 1 and 3 in equation 2, we have mu Cp is equal to delta U by delta T plus mu R. Let this be equation 4. Now, as a second case, let the same gas be heated at a constant volume. If the heat absorbed by the gas is delta Qv, where the suffix V indicates that the heat is absorbed at a constant volume, and the temperature change is delta T, then delta Qv is equal to Cv into mu into delta T, or delta Qv by delta T is equal to mu into Cv. Let this be equation 5. But at constant volume, the work done by the gas delta W is equal to 0. According to the first law of thermodynamics, delta Q is equal to delta U plus delta W. As delta W is 0, we have delta QV is equal to delta U. Let this be equation 6. From equations 5 and 6, we get delta U by delta T is equal to mu into Cv. Let this be equation 7. Note that in both processes, we have taken the change in the internal energy of the gas as delta U. This is because in both cases, the change in the temperature of the gas is delta T, and the change in the internal energy depends only on the change in the temperature of the gas. From equations 4 and 7, we have mu Cp is equal to mu Cv plus mu R, or Cp minus Cv is equal to R. This is the relationship between the two molar specific heat capacities of an ideal gas. The cylinders shown are oxygen cylinders. Usually, when filled with the gas, all these cylinders contain equal quantities of oxygen. But how can an empty cylinder be filled with exactly the same quantity of oxygen? The ideal gas equation is PV is equal to mu RT, where P is pressure, V is volume, T is temperature, and mu is the number of moles of the gas. R is the gas constant. Hence, if the pressure, volume, and temperature of the oxygen in different cylinders are the same, they must contain the same quantity of gas. Since the volume of all these cylinders is the same at a given constant temperature, if oxygen is filled to a certain pressure, all these cylinders will contain equal quantities of oxygen. If oxygen gas in a cylinder is treated as a system, we can reproduce the system by knowing the values of some of the properties of the gas, such as mass, pressure, volume, and temperature. The set of values of properties of a thermodynamic system, which are used to reproduce the system, is known as thermodynamic state, and the properties are also called variables. The state of the oxygen gas in a cylinder is expressed by providing values of its pressure, volume, and temperature. If the values are P, V, and T, then the state is represented by P, V, T. Now, consider the general case of a gas in a container and let the state of the gas be represented by PVT. If the variables that describe the state, PVT, have uniform values throughout the system and they do not change with time, the system is said to be in equilibrium state. If A, B, and C are 3 points in the system, and PA, PB, and PC are the pressure of the gas at A, B, and C, and TA, TB, and TC are the temperatures of the gas at A, B, and C respectively, and if the state of the gas PVT is in equilibrium state, then PA is equal to PB is equal to PC is equal to P, and TA is equal to TB is equal to TC is equal to T. Not every state of a system is an equilibrium state. For example, if we suddenly pull the piston up, a vacuum is created above the gas, and the gas in the cylinder starts expanding against the vacuum. This is known as free expansion. During free expansion, the pressure and temperature of the system is not uniform throughout the system, and these values change with time. If P, Q, and R are 3 points in the system, and at these points the pressures are PP, PQ, and PR, and the temperatures are TP, TQ, and TR. Then PP is not equal to PQ, not equal to PR, and TP is not equal to TQ, not equal to TR. And these values at any point change with time. Hence, the state of the gas is not in equilibrium state. If the piston is completely removed, after some time, the gas is in mechanical and thermal equilibrium with its surroundings. If the pressure of the system is equal to the external pressure, then the system is said to be in mechanical equilibrium. And if the temperature of the system is equal to the temperature of the surroundings, then the system is said to be in thermal equilibrium with its surroundings. The variables that describe equilibrium state of a thermodynamic system are known as thermodynamic state variables. For example, if the pressure, volume, and temperature of a given quantity of gas in a container is denoted by P1, V1, and T1, then its equilibrium state can be identified by P1, V1, T1, and P1, V1, and T1 are the state variables of this system. During any thermal process, if the equilibrium state of a system is changed, this is described by a change in the values of the state variables. If the gas in the container is compressed, and as a result if the pressure, the volume, and temperature of the gas are changed from P1, V1, T1 to P2, V2 and T2 respectively, then the new equilibrium state is expressed by P2, V2, T2. As the name suggests, state variables of a system depend only on the state of the system, and they do not depend on the path through which the system is taken to attain this state. All the variables that describe an equilibrium state of a system may not be independent of each other. If pressure, volume, and temperature of a given sample of gas in a container describe its equilibrium state, then the volume of the gas depends on its pressure and temperature. The relationship between state variables is called an equation of state. For a sample of mu moles of an ideal gas in a container, the ideal gas equation PV is equal to mu RT is the equation of state. From this relation, we can understand that of the three variables, P, V and T, only two are independent, and the third one depends on these independent variables. In the case of real gases, the size of the molecule is not negligible compared to the average separation between them. And the intermolecular attraction is also not negligible. By taking the above two facts into consideration, van der Waals has derived an equation of state for a real gas, which is P plus A by V square, V minus P is equal to mu RT. where A and B are constants. The constant A is related to the average force of attraction between the molecules, and the constant B is related to the total volume of the molecules. The state variables discussed so far are of two types: extensive state variables and intensive state variables. A state variable that depends on the size of the system is called an extensive variable. For example, the volume of a system depends on its size, and hence it is an extensive variable. Mass and internal energy are other examples of extensive variables. On the other hand, an intensive variable does not depend on the size of the system and has a uniform value in different subdivisions of the system. If a system of gas in a chamber, that is, in an equilibrium state, is divided into two equal parts, the variables that remain unchanged are intensive, and variables whose values are halved are extensive. We can see that there will be no change in the pressure, density, and temperature of the gas. Hence, pressure, density, and temperature are intensive variables. On the other hand, mass, volume, and internal energy are halved, and hence these are extensive variables. In any thermodynamic equation, quantities on both sides of the equality symbol must be either extensive or intensive. For example, the quantities on both sides of the following equation are extensive. Delta Q is equal to delta U plus P delta V, where delta Q is the heat exchanged, delta U is the change in internal energy, P is the pressure, and delta V is the change in volume of a gaseous system. Here, as delta Q depends on the mass of the system, it is extensive, and though P is intensive,